Hello everyone, so today we're working on a linear algebra problem. We're working with a transformation and we're trying to find a matrix representation for this transformation T with respect to two bases, which we call B and B prime. Well anyways, we have find matrix T going from B to B prime, and usually that's read right to left instead of left to right. For this transformation T that goes from R3 to R2, and the transformation is defined as T of x1, x2, x3 is equal to x1 minus x2 plus x3, comma 4x1 minus 3x3. And yeah, you're always gonna, when you're being asked this question, you're gonna have two bases to work with. One is the base for the domain, and the base for the range. So the basis for the domain is 1, negative 1, 2, 0, 4, 1, 1, 0, negative 5, and then you have B prime, which is the basis for R2, 1, 4, and 5, 7, okay? And the way this works is a matter of, it's a few steps here. It's not too bad, it's okay, but it is can be a little tedious. Just let me say that first. First thing you're gonna do is you're always gonna find the transformation of each of your basis vectors of the domain space. So we're gonna take all the basis vectors in B and we're gonna put them into a transformation and see what we get out. So we're gonna take 1, negative 1, 2, 0, 4, 1, and 1, 0, negative 5 and put them all in our transformation. And I went ahead and computed each of these. And when you plug 1, negative 1, 2 into T, you get 4, comma, negative 2. When you plug in 0, 4, 1 to T, you get negative 3, negative 3. And when you plug in 1, 0, negative 5 into your transformation, you get negative 4, 19. Okay, so always do that. That's like really important. All right, here's what you're gonna do next now. You're gonna take each of those results for those transformations under those vectors, and as a linear combination of vectors 1, 4, and 5, 7. So all the images of all the basis vectors you have, you're gonna write as a linear combination of the basis vectors. In our case, the base of the range. In our case, the basis vectors of our range are 1, 4, and 5, 7. And as I wrote here, typically this involves solving a system of equations. Sometimes it's pretty easy. Sometimes it's just something like you can see like right away. But often it is the case that no, you need to do a little more work, which is the case here. So we're looking to, at the end of the day, write the result of each R space as a linear combination, as I said. And you have these systems of equations. I have three equations here. 4, comma, negative 2 equals C1 times 1, 4 plus C2 times 5, 7. Negative 3, negative 3. The next image result is equal basically to a linear combination of the same vectors, except the coefficients are different. And minus 419 follows suit as well. It's equal to E1 times 1, 4 plus E2 times 5, 7. And your task basically is to get these coefficients. So what I did, in order for us to solve for these coefficients, I'm going to simplify a bit. I'm going to use the first equation here as an example. You don't have to, I'm not going to do it for all of them because I don't want to bore you here to death. But what you're going to do here is you're going to distribute the C1. The first equation, I took C1 and C2 and distributed them into the vectors. And then what I'm going to, so that's what you have right here, where I have 4, negative 2 equals C1 times 4C1 plus 5C2, 7C2. And what I'm going to do now is I'm going to simplify this even more. I'm going to add the like component. So I'm going to add C1 and the 5C2 together. That'd be the first component. And then 4C1 and a 7C2 together. And just basically using operations of additions of Rn as a vector space, using the usual addition, basically. And I'm going to now set up a system of equations. How do I do that? Well, if you tell me two pairs of things in R2 equal each other, then the first component of the pair equals to itself, and then the second component equals. Okay, so I'd have this system of equations you see here. C1 plus 5C2 equals 4. 4C1 plus 7C2 equals minus 2. Come out of that. And similarly, you would do the same thing for the other vectors, the other equations that I had. And what you can do though is you can put all of this in one system of equations actually. Well, not one system, into a whole, I say matrix here, okay, like an augmented matrix. And the reason we can do that is because if you look at the equations that you see here, the systems, if you were to solve them using a matrix for each individually, the coefficient matrix would be the same, and all the operations that you would use to row reduces would be all the same, okay? So that's what I did over here. This is like the coefficient matrix, and these are all your values here. And what I did here was I went ahead and row reduce, as you can see, doing a bunch of stuff. So yeah, so this is the usual things that you use in linear algebra. And finally, once you row reduce to the identity, whatever's left there, that is the matrix that you're looking for, okay? So the big deal here is, going over the main steps here, is you're gonna go ahead and take each of your basis vectors, put them into your transformation for your basis for your domain, and you're gonna get some outputs, and each of those outputs you need to write as linear combinations of the basis vectors for your range space, for like we say the W here. For in this case it's R2, and you need to solve for these constants essentially. And at that point it's more just usual, like working with matrices and like using the techniques that you learned. I prefer to use row reduction here, as you saw, and whatever you have left is your matrix that you're looking for. Now, just as a quick comment on what you use this for, often it is the case that it's easier to work with a matrix representation of a transformation than it is with the actual transformation. Not in this case. I would say it's easier to use the actual transformation, but in some cases it is. And for example, one application is to find the image under a transformation. So for example, here I'm saying T of 413. How can I find that using that? And I will make a video on how to do that, but I just wanted to give you a heads up on like what's the purpose of doing this, okay? All right, well, thank you for your time, appreciate it.